second paper will be presented by Jiachen Xu, and he's a third-year PhD student. His research interest is mainly in fuzzing and software engineering, especially for complex targets like the Linux kernel. And today he will present mock optimizing kernel fuzzing mutation with context-aware dependency. Thank you.
Thanks for introduction, Bianchi. Good morning, everyone. I'm Jiachen Xu. I come from Zhejiang University. Today, I'd like to share our fuzzing work that optimizes kernel fuzzing with context-aware dependency. It's a joint work by Zhejiang University, UCLA, and Georgia Tech. The OS kernel plays a crucial role in the overall security of a computer system. Due to a large code base and complicated architectures, kernels have been plagued by vulnerabilities. Vulnerabilities in the kernel can allow attackers to access sensitive information, disrupt normal functioning, or even compromise the entire system. Coverage-guided fuzzing has been an effective and preferable testing technique for vulnerability discovery. It repeatedly feeds generated inputs into programs and discovers complex vulnerability with the help of programs, feedback, and sanitizers. Regarding kernel fuzzing uses syscall interfaces as entry point. The test cases consist of syscall sequences. However, it's non-trivial to trigger kernel vulnerabilities. Despite recent progress, like Healer, CVEs, constructing high-quality inputs is one of the bottlenecks constraining efficient kernel fuzzing. The difficulties arise from several aspects. First, for instance, due to complexity of kernel codes, the shared variables often lead to intricate dependencies between syscalls. These dependencies can be both explicit and implicit. Moreover, to trigger kernel vulnerabilities, syscalls must adhere to specific execution sequences to establish specific kernel states. The execution number of syscalls corresponds to a vast search space, rendering blind enumeration impractical. For example, syscaller defines more than 4,000 syscall interfaces, with each test case containing multiple syscalls, which result in a substantial search space. Therefore, the dependencies among syscalls are crucial for input senses and significantly affect the efficiency of fuzzing. However, existing fuzzing methods exhibit deficiencies in dependency modeling. In a 24-hour experiment, test case generated by syscaller and Healer were minimized. Only 8% of them contain more than 3 syscalls. This indicates their difficulty in generating complex inputs. This issue indicates their difficulty. This issue arises from 2 main factors. First, these methods only consider the most recent syscalls during dependency recognition and seed mutation, disregarding the influence of the context. Such a context-free strategy constrains testing effectiveness. Fuzzers maintain seeds containing rich dependency relationships. However, existing methods seldomly fully utilize knowledge within the corpus. So, context-aware dependency is desired, but how to automatically model and utilize context-aware dependency for better fuzzing? To address the challenge, we propose a context-aware dependency-guided kernel fuzzer named mock. We design a neural network model to capture the context-aware dependencies without a pre-positioned training set. It explores the generation and the mutation of test cases under the guidance of syscall dependencies, enhancing the quality of test case generation. Moreover, we introduce a mutation strategy scheduling mechanism based on multi-armed bandit algorithm to adaptively balance exploration and exploitation. This is the overview of mock. To be specific, first, we introduce a context-aware syscall dependency modeling method based on a neural network language model. Mock initially explored the kernel space by randomly or heuristically combining different syscalls to form test cases. As the testing progresses, mock dynamically collects interesting test cases generated during the runtime. Meanwhile, it employs a minimization algorithm to distill test cases, establishing a unique set of dependency instances. Unlike traditional pairwise modeling approaches, we propose the context-aware dependency relationships, which defines the conditional probability of syscall dependencies for the given context. The model learns dependencies from the instance set and the separately provided high-quality seed set, and periodically being updated to adaptively adjust the relations based on heuristic data. Furthermore, mock integrates context-aware dependency to investigate dependency-guided test case generation and mutation. For a given seed, mock randomly selects a mutation position within the sequence. The syscall subsequent before the mutation point serves as a preceding context, determining which syscall will be affected by it, while the syscall subsequent after the point serves as the rearing context, determining which syscalls will affect it. During the test case generation, the contexts are sequentially fed into the model, and the model outputs the conditional probability distributions of the candidate syscalls corresponding to the contexts. These distributions are merged based on context weights, with the top k probabilities selected as the final candidates. Finally, the father randomly selects a syscall from the top k candidates according to their weights and insert it into the mutation point, filling in the corresponding parameters to complete the test case generation process. In the end, striking a balance between the exploration and exploitation is crucial for ensuring efficient kernel fuzzing. Excessive pursuit of exploitation may lead to falling into local optima, limiting the diversity of corpus and mutations, and consequently impacting the overall testing performance. To address the challenge, mock employs a scheduling mechanism based on multi-armed bandit algorithm. During the testing process, mock will record the timestamp, the number of selection for each mutation strategy, and the number of new code coverage discovered. Once the exploration phase is completed, the further transitions to the exploitation phase. At the onset of the exploitation phase, based on the data collected during the exploration phase, mock evaluates the performance of each strategy using the UCB1 algorithm. The strategy with the best performance is selected as the sole mutation strategy to be continuously employed during the exploitation phase. After the exploitation phase concludes, mock reverts to the exploration phase, and thus completing a cycle that spans the entire fuzzing period. And now I will introduce our evaluation. We try to answer the following questions. The first, our experimental settings are as follows. We evaluate mock compared with 3 baseline fuzzers, syscall, sysvegas, and healer on 3 versions of Linux kernels. All the fuzzers use the same configuration of kernels and the resources without initial seeds. Each evaluation lasts for 7 days and is repeated 5 times. To answer the first question, we evaluate mock's capability of exploring kernel code coverage with the same time budget. Comparing to other baselines, mock averagely achieves 7% coverage growth and 1.71 acceleration. Regarding the effectiveness of context-aware dependency, we investigate minimized test case and the performance of context-free and context-aware dependencies under various contexts. We found that mock can produce 50% more interrelated syscall sequences. It facilitates more interrelated input senses. To evaluate how the various setups contribute to the efficiency of mock, we conduct experiments by feeding the fuzzers with initial seeds and integrating the pre-trained context dependency model with mock. In the process, the corpus is collected from sysbot and previous runs. The results show that both settings can help reduce the warm-up time and accelerating fuzzing process. To demonstrate mock's efficiency in vulnerability detection, we conduct experiments on an earlier version of Linux kernel 5.10 and compare the number of unique vulnerabilities reported by each fuzzer. Mock finds 15% more vulnerabilities than the state-of-art fuzzers. Besides, mock has better performance regarding detecting the complicated vulnerabilities that are triggered by no less than 5 syscalls. We also evaluate the capabilities of mock in discovering real-world vulnerabilities. We run mock on several versions of Linux kernels. Our fuzzers has uncovered 15 unique vulnerabilities in total, of which 4 are confirmed and 4 are fixed by Linux kernel developers, and with 2 CVE ID. Sorry. I missed how go back to the previous slides. Thank you. We also do further analysis to measure the contribution of each of our design. The stepwise analysis shows that combining both the dependency-guided mutation and the task scheduling brings considerable benefits. And for each component in the mock, it has a crucial role to play. Besides, in the process, the introduced overhead is acceptable, about less than 7%. We briefly discuss future work here. In this work, we have used a lightweight neural network structure for a trial, but more complex neural network may potentially enhance the performance. Besides, it will be difficult for mock to capture concurrency dependency if 2 syscalls are concurrently executed. This is because the minimization algorithm does not apply to concurrency scenarios. As a future work, it is interesting and challenging to model the concurrency dependencies on complex system. In conclusion, we present mock, a kernel fuzzer equipped with the context-aware dependency, which selects proper syscalls according to the context, so as to produce in-depth input. In this regard, mock learns the dependency by training a model on the dynamically collected corpus and applies a context-aware mutation schema. We conduct comprehensive evaluations showing that mock performs effectively in achieving branch coverage, producing more interrelated syscall sequences, and discovering bugs that than the state-of-the-art kernel fuzzers. And that's all. Thank you. Any questions?
Okay, thank you for the presentation. We have time for some questions.
Hi, Abhik Rajchodhuri from NUS. So thanks for your presentation. So you mentioned during the presentation that you are moving between the exploration and the exploitation. So one would expect that you, it's not like first you do exploration and then exploitation. You have exploration, maybe exploitation, then you move on to exploration of other contexts and so on. So would you comment a bit on that, or is it like one shot? You just have exploration followed by gradual move towards exploitation? Because in a context-aware kind of setting, you would not gradually move just from exploration to exploitation. To design the fuzzer, you would need to alternate. So I was just wondering how that went. Thank you.
Thank you. Yes, we are not the first to propose a balance to propose to balance the exploration and exploitation in fuzzing stage. But different from previous works, the design of balancing exploration and exploitation in our work is designed for our context-aware dependencies. In other words, if we drop the design, the learned context-aware dependency could be finally ineffective. Yes, we may lead to a local optima because we do not use pre-positioned corpus. Yes.
Yeah, we can take it offline. I think you can do better than you can exploit the context better. I can suggest something maybe offline. Yeah, thank you.
How to go back to the previous slide?
The red one. The red one.
Which button?
The red button.
Okay, thank you. You mean this slides? Yes, okay. Thank you. Thank you. Thank you.
We have time for another question.
Hi, Roland Yap, NUS. Maybe just to clarify, because maybe I missed something. So did you investigate the differences in the context? Like, you know.
Sorry, I can.
Did you investigate the differences in context? Like, you know, shorter context, larger context, longer context, that kind of thing?
So sorry, can you say I didn't catch you?
Oh, did you investigate in the experiments parameterizing the context? So you could look at, you know, larger context, smaller context, longer context, shorter context.
In the domain of kernel fuzzing, the context is compared with other domains. The context in the kernel fuzzing is relatively small. Yes.
But I mean, for example, you can look at system call length, right?
Syscall language.
System call length. How many system calls? Context.
As our work is built on top of syscaller. Syscaller defines more than 4,000 syscall interfaces, which means
no, not the number of interfaces, the number of system calls.
Number of system is about.
No. I mean, if you have syscall A followed by syscall B, that's 2.
Like the length.
The length. The length of the system call sequence.
Less. You mean less? Yes. The length of system sequences varies from test case to test case. It's about 8 to 20, maybe. Yes.
Right, but did you investigate differences in the length? Like you could parameterize the length and say that, oh, what if we just do 2? What if we do 10 and so on, right? Maybe take it off.
Okay, I guess
Okay,
you
thank
can
Or
discuss
maybe we
this
can
more
discuss later. Yes, thank you.
later. Okay, we have time for a quick question.
Yeah, hi, Lucas from Santa Barbara. I was wondering, did you investigate any simpler machine learning models than the one you've come up with? Like, I don't know, decision trees, anything that you evaluated against?
Can you say again?
Did you investigate any simpler machine learning models for your system call selection probability distribution that aren't a full by LSTM? And what was the performance if you did?
Yes, we use LSTM as the model to capture the context-aware dependency.
Did you try easier models?
No, we we directly using by LSTM as our dependency model. Yes, we have not tried a more complex or more naive model. Yes.
Okay.
Okay, thank you for your presentation.
Thank you.
And